Hi, Carl Winkler here at Lectrosonics, and I'll be your instructor on wireless microphone technology and the 7 most common problems that you're likely to run into and how to solve them. So to get started, what I'd like to do is give you a little bit of background on me so you'll know where I'm coming from. I started out in live sound in the early 1990s working for the U.S. Air Force Band, Airmen of Note, Big Band Jazz Ensemble, and we toured all over the United States, and we even took the tour over to Japan. It was a fantastic experience for me, a lot of hard work, a lot of hot summer days out in the sun and so on. And this picture here shows me at the Yamaha PM3000 console in the summer of 1992 down by the Potomac River in Washington, D.C., right before a big festival. So I had plenty of experience on the road and used all analog equipment back in the day and analog outboard gear, and wireless microphones were pretty rudimentary by today's standards. The first system that I used was this Vega wireless microphone in the VHF band, and we'll talk about the difference between VHF and UHF here just in a little bit. But this system only had one frequency that it could tune to. So if it worked, great. If it didn't work, we put it back in the box and we use a hardline microphone. And that's the way systems were then, even for the highest quality systems. What is RF? Radio frequencies. What are we talking about here? I want to give you a little bit of background because then the 7 problems that we'll talk about and how to solve them will make more sense. So, first off, the radio frequencies. This is everything from your FM radio, walkie-talkies, TV frequencies for transmission, and so on. It's all part of the electromagnetic spectrum. And this chart I'm showing you here kind of indicates the relationship between the size of the wave and the frequency that we're talking about. Similar to sound waves, the lower the frequency, the longer the wavelength, and this is also true for electromagnetic waves. Okay, so at the far left there are the very low frequencies that are, gigantic wavelengths, the size of buildings. Then you get up into the wavelengths that are like the size of people, and then smaller and smaller and so on. So I wanted you to understand that there's a physical relationship between the wave frequency and the wavelength. Okay, so and notice that visible light is part of that same electromagnetic spectrum, as well as X-rays, gamma rays, and so on. It's all part of this electromagnetic spectrum. So what is VHF and what is UHF? Well, you probably already figured this out, that VHF is very high frequency, so-called, and UHF is ultra high frequency. So where do these fit in? This chart shows you that VHF is above FM radio. FM radio is 88 megahertz to 108 megahertz, and the VHF band that we're concerned with starts at about 174 megahertz and goes up to about 216 megahertz. And then UHF, at least as far as we're concerned, starts at about 470 megahertz and goes up in the United States now to about 700 megahertz, although we don't have access to the top part of that anymore for wireless microphones or for TV broadcasts. Then there's the other pieces of spectrum that we do sometimes use with wireless microphones. There's stuff in the 2.4 gigahertz range, there's stuff up in the 5 gigahertz range, but I wanted to show you mainly that even though you have all that electromagnetic spectrum and all that radio waves cover a very wide range of spectrum, there's only a few little tiny parts of all of that that we get to use for wireless microphones, which makes it part of the challenge for what we do, is how to fit all the channels that we need to get to work into a tiny piece of spectrum. And we'll get to that as well. So here's a baseline. Here's the TV channels where our TV broadcasts, they call it OTA or over-the-air broadcasts, and more people are watching online and streaming like Netflix and Amazon Prime and things like that. But there's still TV broadcasts, and this shows you the TV channels and the frequency ranges that they cover. In the United States, each TV channel takes up about 6 megahertz of spectrum. So there you go. And this is what we have to fit into. Another point I'd like to make is that everything that we do in our business of audio for churches and other live types of events, we are sharing spectrum with somebody, no matter which part of the frequency range that we're in. So what I'm showing you here is an illustration of a spectrum scan done quite a while ago, I think 2002, where you see that there are analog television stations broadcasting, which we no longer have in the US, and also digital television stations. So the analog ones are the ones there with the two spikes, the picture carrier and sound carrier, and then the digital television looks more like a big block of frequencies across all 6 megahertz. So where do we fit in? Exactly in between those. So those red lines are our, what are called carriers, our wireless frequencies that we're using. We've got to find open slots in between TV channels to put our wireless microphones and in-ears and communication systems. So it becomes quite challenging in dense areas where there's a lot of TV channels and we have a big production we want to put on using a lot of wireless mics. As you can see, it gets very tough. And we'll cover this in a lot of detail, just how to do that. Okay, so we've covered the basics of wireless spectrum and how our wireless microphones fit into the bigger picture of what's going on out there with the TV broadcasts and other sources. So let's look at the 7 most common problems that you're likely to encounter using wireless microphones and ways that you can solve those problems. So the first one is lack of frequency band planning. This is a concept I want you to definitely take away from this material, is what is band planning and what does it mean to you and how can you master this concept. So the main concept with band planning is that you want to put your different kinds of systems, wireless microphones, in-ears, communication systems, and anything else that needs to be wireless, they should be in different parts of the spectrum so that they do not overlap each other and cause interference between the systems. If you have a very powerful in-ear transmitter, for instance, right next to your very sensitive wireless mic receivers, and they overlap in their bandwidth, you can have problems. So that's the concept of band planning, is to keep these different things separated. So the overlap causes problems, as I said, and just think about having slots for each of those different types of systems. Now, if you've been paying attention, you'll notice that with all the TV broadcasts going on, there's already a lot of spectrum eaten up. So recent wireless mic systems have been wider and wider tuning bandwidths so you can work your way around the existing TV broadcasts. However, it also means they're likely to overlap. So that's going to be a challenge. Okay, so that's the basic concept of frequency band planning. Now, one resource that's very important to take a look at is this one here I'm showing you on the screen. This is a tool that you can use on the web to determine which TV channels are active in your area and which channels might be open. So if you're about to buy systems, I would use this. If you're about to rent systems, I would use this. And certainly if you're about to run a large, complex system, this is a great resource. So take a look at this. And it also will tell you whether or not frequencies that you're likely to use, or the systems that you have, whether or not those are legal to use anymore. In the last 15 years, there's been 2 different frequency spectrum auctions that have happened in the TV bands. The first one was in the early 2000s and culminated in 2010, and that took away the 700 megahertz band between 698 and 806 megahertz. And then we had a more recent one that concluded in 2017 that determined that the 600 meg band, everything from 614 to 698, was auctioned off. And we have almost no access to that frequency band anymore legally after this July in 2020. So these are important things for you to know. You may have older systems that are no longer compliant with the law about frequency spectrum. And this website here, antennaweb.org, will tell you that answer. Okay, so the next thing to figure out how you're going to band plan has to do with RF scanning. And there's a number of ways that you can accomplish this. You can use a frequency spectrum analyzer, which is a separate device, and I'll show you an inexpensive one here in a minute. And the other way to do it is with the receivers themselves in your wireless mic system. Most receivers today, with accompanying software, will do some kind of a scan so you can see what's active in your local environment. This is very important for band planning and the subsequent steps that we'll go through later, showing you more detail about how to do frequency choice. Okay, so just be aware that every city looks different And so a band plan that makes sense for Minneapolis will not make sense for even Chicago, and certainly not for New York, Atlanta, and so on. So you want to look at what's happening in your local area, and a frequency scan is the best way to do that. So the RF Explorer. This is a low-cost tool that will give you a very good idea of what's happening in your local spectrum in a simplified manner. This is not a $10,000 analyzer, it's just a few $100s, but it's a great tool to have. I keep one myself, I have it in my bag, and I take it everywhere with me because it's such a great resource. And there is a software package you can get to go with it that'll give you a more detailed look at the scan data that comes out of the scanner. But even handheld, this can be a very useful device. So I recommend that if you're using a lot of wireless systems, to go ahead and get an RF Explorer. Another very important thing to remember with band planning is to consider all RF sources. Can't tell you how many times I have been in a place where they've done the wireless microphones and maybe the comms, but they forget about the in-ear monitors because they don't somehow make the connection that it's all part of the same spectrum. Doesn't matter which direction it's going, either from backstage to the band or from the band to the backstage. It's all spectrum that needs to be shared between all these units. If you've got in-ears, if you've got instrument wireless, backline wireless, vocal mics, you name it, comm systems. If there's going to be a skit and they're wearing wireless, that has to be included. So capture all sources before making your total band plan. So I mentioned this a minute ago, what's happened with the spectrum auctions in the past few years. And so this is kind of a detailed look at the remaining spectrum we have in the United States and how it's chopped up into those 6 megahertz TV channels. And then above TV37, which by the way is reserved for radio astronomy, there's a couple tiny slices in the 600 megahertz band, but they're tightly restricted to a max power of 20 milliwatts, which isn't much, and only a few channels can fit in there. So most wireless systems today, if they can tune outside of those slots or if they have more power than 20 milliwatts, they either need to be updated with firmware or you're not allowed to use them anymore. So just keep that in mind. The laws keep changing and it's in your best interest to be aware of this. And again, I gave you a resource a few minutes ago how to keep track of that. Okay, so what I have here is an example frequency band plan for you to ponder. This is just an example. But it gives you a good idea how a professional event would be band planned between the different types of systems. So let's say you've got some IFB, that's one-way comm systems. It's sort of like an in-ear system, but a mono audio signal. IFB, so there's Comtex and probably another brand or two down there. 72 to 88 megahertz. This is below FM radio. Not a super high quality place to put wireless mics, but it's fine for simple communications to camera crew and things like that. Then you get into the high band VHF, like I mentioned earlier, 174 to 216 megahertz. That's where you might put your RF intercom systems, receivers, and maybe your IFB transmitter system if you're using the Electrosonics VHF IFB. Next up, 450 to 470, that's your land mobile radio or walkie-talkies. And those can be very high-powered devices up to 4 and 5 watts, which can be a real problem if they're right next to your wireless mic receivers. So you want to keep those away if you can and keep the power of those systems down as low as possible. Most live events do not need 5 watts of power out of a walkie-talkie. 1 watt would be more than enough, and maybe even a half a watt would cover an entire area. So next up, 470 to 495 megahertz. We're putting some wireless mic receivers, and most companies these days make systems in that frequency band. Next up, 512 to 555 might be more intercoms. Then 565 to 608, more wireless mics, and again, most manufacturers are making systems there. The Electrosonics B1 band, as an example, covers that frequency range. Then there are some systems in the 902 to 928 range. This is one area where you're going to share spectrum probably with wireless DMX for your lighting and maybe a couple other things. There's even a cordless phone in that band. So, and a number of your wireless intercoms would be in that frequency band. Then 941 to 960 is reserved for license holders only, and typically that's going to be broadcasters like your news crews. So for instance, Electrosonics, we've sold a lot of systems in that band to news organizations like NBC when they have their news crews go on site. And it's not accessible to anyone without a Part 74 license. 1.4 gigahertz is a special area that you need a temporary license to use, but for some large events like the Super Bowl, they might get a license to have some interview microphones in that frequency range. 1.9 gigahertz is the DECT band. It was originally developed for wireless telephone type headsets, but now there's a few wireless mics out there. But I would say that based on the technology, the latency, which means the delay in the signal, is rather large and probably not a good idea to use those systems for live sound. But for like camera interviews and stuff like that, they might work well. 2.4 gigahertz, we get a lot of questions about that. It's usable, it's an unlicensed frequency band worldwide. Wi-Fi is there. There are some wireless mic systems there, but all I would say is that you want to keep your channel counts there to a minimum. Any more than a handful of channels becomes very problematic because of the unpredictable nature of that Wi-Fi frequency spectrum. But there are systems there. If you only need one or two, it might work okay. And then 5 gigahertz, the company Neutrik, they make a point-to-point system for very large-scale sound systems. Point-to-point means from like a mixing console, you could transmit a wireless signal out to a delay speaker tower, and it would maintain fidelity. These are very large. They're not body-worn. But this gives you a clear idea of how you might set up the band choices for all the different types of systems that you're using that are wireless. Okay, so we've covered band planning in enough detail for you to understand the concept and realize how important it is. The next thing I want to talk about that's very important and often done incorrectly is receiver antenna placement. If you put the antennas for your receivers in the wrong place or use the wrong kind of antennas, you can definitely have an effect on the reliability of your wireless microphones. So let's look at a couple things. I call these antenna don'ts. I've taken some pictures over the years, and some of my colleagues in the industry have shared with me some pictures that they've taken. So this is one I took on a film set, actually. I won't name names. But what you see here is a cluster of antennas all within a few feet where you have both receiver antennas and in-ear and IFB transmit antennas. This is definitely a no-no because your receivers are very sensitive, and if they are bombarded with strong RF signals, even if those RF signals are out of their frequency band, they can reduce sensitivity of the receiver and reduce your range. So in this particular case, they told me that they were running into some problems with dropouts with their wireless mics, and it seemed to start happening after they added the active antenna, the one on the far left in the picture there. So we dialed the amplification of that antenna down. We'll get into details about that. And I suggested that if at all possible, they should separate their transmit antennas onto a different stand and have your receiver antennas physically separated by as much as possible. So I don't know if they've done that, but I haven't heard any complaints. So I have a feeling that they may have followed some of that advice. Here's another one that's fairly common, is to see the receiver antennas plugged onto the back of the receiver inside of a metal enclosure, and they wonder why the range is terrible. So this would be the kind of thing if you had receivers mounted in a rack at front of house or even backstage, and the antennas are not exposed to the air where they can have a line of sight to your transmitters. The range of this was terrible. So what we recommended in this case was to simply remote the antennas with short coax cables and mount them on the outside of the rack. Problem solved. Simple as that. This shows you a quick photograph I took with my phone of what a scan looks like when the antennas are inside the rack. So not only is the range shortened because RF doesn't go through metal very well, but all the other equipment in the rack generates a lot of RF noise. Anything with a processor in it, anything with the A to D converters in it or a DSP is going to create RF. It's not high power and it doesn't go very far, but if your antennas are right there, this is what the scan looks like. So after we moved the antennas to the outside of the rack, I took another picture of the scan, and this is what it looks like. Much better, much more room to put our wireless mics and in-ears and comms into that same space. So this is the same physical space, same RF scan, except now the antennas are outside the rack. You can see what a difference that makes. Keep in mind that antennas have directionality. That means that they're more sensitive in some directions and less sensitive in others. Even omnidirectional antennas, like the one I'm showing you here, this is a Electrosonics SNA 600A dipole omnidirectional antenna, but it's omnidirectional in the lateral plane like this, just like the picture shows. So the maximum sensitivity is going to be this way, and the minimum sensitivity is going to be from the top and bottom of the antenna. So even an omnidirectional antenna is not omnidirectional all the way around like it is for an omnidirectional microphone. It still has nulls, or places where there's very little signal, and strong sides where you get good reception. So placing these antennas is important, how you place them, where you place them. And notice that these polar graphs on the antenna data sheet will show you the polar pattern for those antennas, just like the data sheet for a microphone will show you the polar pattern of a microphone. Let's look at a different kind of antenna. These are the ones you see a lot in larger installations and tours and things. These are a directional antenna, sort of like a directional microphone. They're going to reject signal from some directions and pick up stronger in the forward area. Now, these are not a laser beam. They have a directionality, but it is about 75 degrees, okay, from that center point in the lateral plane, and sort of like a cardioid microphone. And from the vertical, they're more sharply defined, kind of like a hypercardioid microphone. So one of the tricks that a lot of people overlook with directional with directional antennas, is to point the null towards something that you don't want to pick up. So let's say you've got a strong set of TV towers just outside of town on a hill. Well, you don't want those signals to get into your antennas. So you could position your antennas to where the nulls are pointed at the undesired RF signals. That'll give you increased signal to noise in your RF chain. That is another important concept. But like I said before, polar patterns are in the microphone data sheets. So take a look at those and think about how you might use the nulls to get better RF signal to noise. There are some specialized antennas that you probably want to know about, including helical antennas, and these can be very handy when you have a lot of reflections in a space. If there's a lot of metal surfaces, helical antennas will generally give you better performance. And the one I'm showing you on the left is a really unique design by RF Venue. This is a collapsible helical antenna. It's got a big metal spring inside and then a Cordura nylon exterior that folds up flat. So they're great if you have to pack them up and store them or move them to another location. Some helicals are fixed and rather large and cumbersome. Doesn't matter if you're never going to move them, but if you are, that's a good choice. And then on the right is another antenna from Electrosonics called the PCA 900. This one is good from 900 megahertz to 1 gigahertz. It covers both the 902 to 928 frequency band and the 941 to 960 frequency band. And RF is RF. If you've got another brand that are in either one of those frequency ranges, this antenna would still be a good choice. And it's a semi-directional. It's got like a wide cardioid pickup pattern. Very handy antenna and very small. It's only about this big. Okay, so we talked about the basics of antennas. Let's talk a little bit more about where to put them. And the main concept I want you to come away from this with is line of sight. That means the antenna, the two antennas between your transmitter and your receiver antennas should be able to see each other. So radio waves travel a lot like light waves and can be blocked in a similar fashion. So if there's anything like a large concrete structure, an automobile, brick walls, anything really dense, in between, people, for that matter, are mostly water, and water absorbs RF. If there's anything in between your receiver antenna and your talent antennas, range will suffer. So this is the reason why often you see receiver antennas placed fairly high, and 10 feet up is a good rule of thumb. The reason for this is it'll look over most people who are standing nearby and directly down onto the talent. The secondary concept here is called the Fresnel zone. This means that RF also doesn't travel like a laser beam in between your transmitter and your receiver antennas. It sort of has an envelope like a giant oval or a football, and anything that encroaches on that shape that's large, dense, again, people, cars, set pieces with a wire mesh, anything like that, can reduce the range of the system. So you want to try to keep that path as clear as possible so the RF signal has a good chance to get there and be picked up nice and solid. So the picture on that slide shows you vertical mounting of 2 directional antennas for a church. So there you see that they're pointed down towards the area of activity where the transmitters would be used, and they're separated by a certain amount of distance so that you have diversity. And we're going to talk a little bit more about diversity reception, but it's another concept that you need to know. It just means that the 2 antennas are going to pick up a different mixture of direct and reflected signals from your transmitters. So you do have to have some distance, and the amount recommended varies, but at least 1 wavelength, but generally more. So I typically recommend separating them by between 10 and 14 feet if you have enough room to do that. That'll give you the best possible reception. Okay, let's move on. The number 3 issue that we run into most often that causes problems in wireless mic systems is bad RF gain structure. Now, if you've taken your audio basic class, you understand gain structure. That's setting your mic preamps or your line level inputs and not overloading that stage, and then not boosting everything with your EQ to the point where it overloads, and then making sure your output from your mixing console or whatever is at the right level. This is the same concept, but in RF. RF is electromagnetic waves, as we talked about, but when it gets into an antenna and into a receiver, it becomes electrical signals. So it's very closely related. So for one thing, you'll need to know that if you do have externally mounted antennas, they're connected with coax cable. And this is, in our business, 50 ohm coax cable, and B and C connectors are the most common type of connector. But through the cable itself, some amount of that energy is lost. So RF coax cables have loss, and the loss is dependent on the type of cable material and the diameter. So here's 4 different examples showing you models from Belden between RG174, which is very thin, about maybe a little less than a 1/4 inch, okay, all the way up to the 9913F7. That's the foam insulator cable that's kind of garden hose-like, quite thick, about a 1/2 inch, and very stiff and very heavy and very expensive. But you can see the difference in loss between the very thin, inexpensive stuff loses 27 dB of power with 100 feet, and the really thick stuff loses only 3.8 dB. That's a very big difference. And this matters a lot when you're doing your RF gain structure calculations. These are simple calculations. Don't let that intimidate you. But we'll talk about it. So there's a rule of thumb that I want you to keep in mind, and that is that antennas, directional antennas, have a little bit of gain. RF amps, sometime if you have a very long cable run, you might need to boost your RF before sending it down the cable. Then you have loss through the cable itself. Then if you're using passive splitters to split your signal into various receivers, those have loss as well. So that's the simple math involved with figuring out your RF gain structure. And the goal is to boost or cut just enough so that you have unity gain through your antenna system to your receivers. More boost is not better, and that's a very common misunderstanding. People feel that they want to boost their RF with an amplifier or an amplified antenna, and that will give them more range. The truth is, there's a chance that you're going to overload something further down the chain in the RF chain, and that's going to definitely reduce your RF performance, cause more dropouts, cause more issues. Okay, so this is the rule of thumb, and I'm going to show you a couple examples of RF gain setting. So in this first slide here, we see ALP 690 amplified antennas, and the antennas are set passively, and so they already native have 4 dB of RF gain. Then we're running 25 feet of RG58 cable, which is a very common coax cable material, and those show loss of about 3 dB at 25 feet. Then we've got a simple passive splitter arrangement where one antenna signal is coming in and then 2 signals are going out, so you can send it over to 2 receivers. Those splitters will lose about 4 dB each. So then we've got short jumpers in the rack itself, and those lose about 1 dB per jumper. So when we get the signal to the receivers, it's about minus 4 dB from where we started, which is a little bit of loss. Now, in my opinion, a little bit of loss with a passive system like this is preferable to too much gain, okay? So, in my opinion, this system is good to go. This will be a very high performance wireless system, assuming that it's good quality components and that the antennas are set up in a good place. Okay, so now, let's say we have to run those cables a lot longer. 25 feet isn't enough to get the antennas to where we want them to be. Let's just say you've got a stage arrangement and you've got antennas up in the girders and you've got to run those lines down to racks somewhere. So now we need 100 feet of cable. If you use RG58, those cables will lose about 12 dB of your RF energy. Same antennas, okay, set passively, same passive splitters and everything else, but now, because of those longer cable runs, at our receivers, we have minus 13 dB, and that's starting to be too much loss. In my personal opinion, 6 dB is approximately the correct amount of loss, or the maximum amount of loss that you'll want in your system. So 13, too much, so I'm marking those with no good. We've got to somehow fix this situation, so let's look at a possible way we could do that. Here, same antennas, same splitters, same receivers, but we're going to replace the RG58 cable material with the 9913 F7. Okay, this is again much more expensive cable, but probably not as expensive as starting to use RF amplifiers in our chain. And again, as much as you can keep the system passive, you'll definitely have the best performance. So here, the cables only lose 4 dB, and so now at our receivers, we have a total of 5 dB of loss, which again is below that threshold of 6 dB to start to be concerned. So in my opinion, this would be a rock solid RF system, and the only change that you just made was to change out the cables for a lower loss cable material. Okay, let's move on to frequency coordination. This is the next most common problem that I run into when I'm looking at wireless mic systems or I'm trying to help someone solve problems. So we've talked about a lot of stuff already, but one of the most important concepts with wireless microphones is frequency coordination. And it's often confused, overlooked, misused, so we'll go over the basics so that you understand the concept behind it and know where to look for resources on how to learn more. And yeah, we should have warned you, there was going to be a little bit of math. That's kind of how it goes with audio. Even if you just wanted to mix, that's how it goes. All right, so what is the concept behind frequency coordination? Well, all wireless microphones have the issue of what's called intermodulation. What does this mean? Essentially, if you've got two different RF signals generated in your transmitters, and those signals get picked up in other devices, like the other transmitter next to it, or a receiver, or an RF amplifier, anything with active RF circuitry in it, there can be phantom frequencies generated mathematically inside these units. It doesn't happen in the air, it happens in active RF devices, like transmitters, receivers, RF amps. So this example here shows you that with a 650 and a 670 megahertz signal entering a nonlinear device, let's just say an RF amplifier as an example, what comes out is the sum and difference frequencies there, and also third order intermodulation frequencies that are very closely related to the two main frequencies we started with. So this gives you an idea that with only two frequencies, you already get two generated third order plus sum and difference tones, second order, and so on. Now imagine what it's like with dozens of frequencies, and the mind boggles. So really the only way to handle this is with software. But here's another slide showing you exactly what happens. These frequencies are related. In fact, with our software, Wireless Designer, you can actually go and physically move, drag and drop your wireless frequencies and see the intermodulation frequencies move around in relation. So it's a great tool to visualize this. But this slide shows you those relationships. All right, so as I mentioned before, there's software packages available to help you solve this challenge. You don't have to do the calculations by hand like we used to in the past using Microsoft Excel or something like that. So Shure makes a package, Sennheiser makes a package, and Electrosonics makes a package. Each one of these software suites is provided with the equipment. Ours you can download from the website as an example. And these connect to your systems and use the actual hardware and will do the calculations to help you avoid having these frequencies step on each other. There's also another package that a lot of us use in the industry. It's called IAS, or Intermodulation Analysis Software, from the company Professional Wireless Systems. Now this one is not free. It's about $500 for the professional version. And it also does not connect to your equipment. It's not an online live system, but it's a great package for pre-calculating your frequencies to make sure that they're not going to interfere with each other. Okay, so that's IAS from Professional Wireless Systems. Don't forget though that these software packages aren't the easiest thing to use in the world, and more experience with them helps a lot. We do have tutorial materials on our YouTube channel. If you look at YouTube/Lectrosonics, there's a video in our wireless side chats playlist that talks specifically about Wireless Designer and how to use it with these systems. So take a look at that if you'd like to learn more about it. Okay, next up, I want to talk about bad transmitter and or mic placement. This is another common problem that we run into. How do we know? Well, people call up and say, you know, I was using this system last week in the same place and it was working great, and now it's not working so well and I don't know what I did differently. So we will ask the question, are you using it differently, or is it on a different person, or is it placed differently on the body on the person? And usually the answer will be yes. We're using it on a person and we're placing it differently. And so maybe the issue is RF shadowing. If you recall, the human body does absorb a fair amount of RF because it's mostly water. So shadowing is an issue. So let's talk about some of the places, good and bad, to put the wireless transmitter. Here's an example that's fairly common. There's some good things about this placement and some not so good things about it. For one thing, if the antenna is touching the body, or if it's touching damp undergarments or even a damp shirt, that kind of thing, some of the RF may be absorbed, even to the point where you start getting dropouts because so much of the RF never makes it away from the body. Another potential problem is that if the pastor puts their arm down, it may cover that antenna. So once again, body absorption is the main thing to watch out for here. One other thing is sweat, which can definitely happen. It might be better to mount the transmitter so it's upside down. So if sweat does drip down the mic cable or down the antenna, it's going to drip off of it instead of into the connector of the transmitter. So there's a couple things to think about. Some of the tricks that we use to help prevent antennas from touching the body or seeing too much RF absorbed is to slip a plastic tube like a straw or a piece of aquarium plastic tubing over the antenna to create an air gap or an insulator. This can help a lot. These tricks are used in a lot of stage productions, for example. So here's the questions that you should ask yourself. Is the antenna contacting skin or damp undergarments? Is it covered by body parts? Is it covered by metallic fabrics? And you know that in a lot of theater productions and some of our work, there's fancy costumes or metallic fabrics, and this can definitely block RF from getting transmitted. And line of sight, is the transmitter and its antenna visible to the receiver antennas? So here's an illustration showing you that although it's often a good place to put the body pack transmitter in the small of the back so it stays out of the way and isn't blocked by the arms, is that you're generating what is sort of like a cardioid pattern. It's a directional pattern based on the position of the body in relation to that transmitter. So this is something to keep in mind, that if you do this kind of mounting, it's best to have the antennas somewhere behind the person to pick them up, to get the best signal. And to some extent, the same thing can happen with a handheld transmitter. As I'm holding it here, it can be somewhat blocked by the body. And in this case, it's better to have the antennas in the front. So what's the solution to both of these problems is to have the antennas looking in from the sides, where no matter which way my body is pointed, you have line of sight between the transmitters and those receiver antennas. So this is a pretty important concept. You saw before we talked about antennas and maybe where to put them, and this shows you the transmitter side of that equation. Okay, topic number 6. The most common issue that we run into is poor audio gain structure. The main issues are that you want to have enough signal above the noise floor, but not so much that you're running into distortion of the signal or limiting in the case of wireless mic transmitters. Almost all wireless mic transmitters have an audio limiter at the front end to keep the signal from overloading the transmission. And so you want to stay away from that, but you don't want to have such a weak signal that the noise floor is a big part of that signal. So let's look at the audio signal chain of your wireless mic system. You're starting out with a microphone, either a head-worn mic, a lav mic, a handheld mic, or an instrument source for that source in the first place. Then there is a mic preamp in the transmitter itself that takes that microphone signal and boosts it, so now it's essentially a line level signal going through the rest of the signal chain. Then it's transmitted. That transmission is picked up by the receiver antennas. Then there's the RF gain we talked about with cable loss, but the audio then goes to either a recorder or a mixer or some other thing, in some cases directly to a camera. And you want to make sure that the signal is nice and clean and strong. Okay, so let's look at the couple areas that matter. In the transmitter, if you don't have enough audio gain, then the native channel noise, it's called, that's the channel of the transmission itself, and all systems have it to some extent. Newer systems, better systems, digital wireless, all has a low noise floor, but there's still noise there. We want to have a good solid audio signal before it gets into that transmission so that you've got a good signal to noise ratio to work with, just like in any other audio system. You can think of a wireless mic system as a microcosm of the audio system. In fact, we think this is so important that we put a little card in with every transmitter that gives you guidelines of how to set the input high enough to just touch the limiters a little bit so that you know that you're getting the maximum signal to noise ratio, and then you should have good audio. Interestingly enough, with analog wireless systems, which are starting to be eclipsed by digital systems these days, but with analog wireless systems, if you set your audio gain too low, it'll actually reduce your range, because the receiver, if it sees a high amount of noise in that signal, it will start to mute the audio. It's called squelching. So the receiver will squelch when that signal to noise ratio gets low enough. So we've done tests here showing that range can definitely be affected in any FM type analog wireless system. Digital systems are fully modulated all the time. That won't be an issue, but you still have to be concerned with getting the signal high enough above the native noise floor of that system. Okay, the 7th most common thing that we run into is the lack of maintenance in the wireless system. And this can take a number of forms, but the general one is you want to keep your system updated with firmware and hardware that is current, modern, and legal. Stay out of those illegal bands that are no longer accessible to us as wireless mic users. But then you have to be concerned about your batteries, your RF cables, your connections, your antennas, if they get weathered, and so on. So here's a list of the most common faults that we see. As I said, lav mics, in some ways, and head-worn mics, they have that very thin cable. The connectors and the cable where the cable goes in can be damaged. Those sometimes need to be cut off and re-soldered, re-terminated. But if it breaks on the element side, that's something that's very difficult, if not impossible, to repair. So it's a good idea to have enough budget in your annual budget for equipment to have a little extra to make sure that you have good, new, relatively new and clean and operational lav mics and head-worn mics. Corroded battery contacts are a problem. You should know this, but just in case you don't, never leave the batteries in the equipment, especially for an extended period of time. Old batteries can leak and cause corrosion. A battery management plan. This is really critical, particularly now that we're seeing more and more rechargeable batteries getting into wireless microphones. It's a wonderful thing. Saves money. They work very, very well. There's not as many batteries going into the landfill. A lot of good reasons to use rechargeables, but you can't just use them and expect them to be the same thing as disposable batteries in terms of convenience. You've got to take ownership. Mark every battery with first charge, first use date, and then replace them on a schedule. I typically like to replace rechargeable batteries if they're lithium ion, once a year is appropriate. If they're nickel metal hydride, I would replace them twice a year. because how much charge they can hold definitely diminishes with every charge. Professional type nickel metal hydride AA batteries, they'll say they can be charged 500 times, and that would be once a day for more than a year. But I find that that's a little bit ambitious. Most of the time, replacing them once or twice a year would be a good idea to make sure that the batteries that you have are going to last as long as you expect them to in your wireless transmitters. Next up, moisture damage. Most wireless mic transmitters are not waterproof. So if they're out in the rain, if they're on a sweaty person, if they get exposed to moisture, they can be damaged. So we do make, and we're not the only ones, but we make a waterproof transmitter called the WM. It's completely sealed. You can also, if you're using standard ones, put them in an aqua pack. That's a type of heavy-duty Ziploc bag. And in some cases, you can put them in an unlubricated condom. In fact, there are black condoms made specifically for theater type applications, which I would consider this to be. So these are all ways that you can seal the transmitter away from moisture if it's going to be exposed to a lot of sweat and that kind of thing. Loose antenna connectors, can't tell you how many times I've run into that where I check through a system and some of those antenna connectors become loose over time, especially if you're doing anything where you're moving equipment around. Even if it's just rolling it down the hall, those vibrations can loosen up those connectors, so check those. Damaged cables, like in this picture here. If the cables get run over by a cart or a forklift, shut in a door, shut in an equipment case, they can be damaged, and it's a good idea to look carefully at your cables regularly to make sure that they haven't been damaged, crimped, smashed, anything like that. On the connector end, if they start getting loose, no good. So cables are relatively inexpensive in the big picture. So make sure that you have good ones, good quality ones from known brands. They're the right kind of cable, 50 ohm, not 75, and that they're in good condition. I mentioned illegal frequencies before, and battery management, it's so important that I put it on here twice. But definitely with rechargeable batteries, it's a great idea to have a battery management policy and train everyone on your team to understand what that means and how to do it. So we've covered a lot of ground with this presentation, and you've seen the 7 most common problems with wireless mics, and now you've got a good idea how to solve those problems or hopefully avoid them in the first place, as well as the introduction to RF spectrum. So you should understand how all this fits together. So in conclusion, having a bulletproof system really is mostly a matter of proper planning and system design, and you've got some good clues how to do that now. Avoiding the common pitfalls, and then frequency coordination. This is not magic. It's math and science. It's well documented. The software packages are out there to help you. And of course, experience matters, and we can help you with that too. And we've got video materials for you to check out. Experience is important. All these tools are fantastic quality today. We have the best wireless we've ever had, but it's in your hands how to use it best. If you do need assistance, by all means, don't hesitate to reach out. My name's Carl Winkler at Lectrosonics. My email address is karlw@lectrosonics.com. Be sure to check out our YouTube channel for a bunch of instructional videos and some interesting product information there as well. And I look forward to meeting you in person sometime soon. Thanks for watching.